Now, let us see variable voltage, variable frequency method of speed control. Okay, so you may ask me, like, others, like, slip control method or kind of many other methods are there, pole change method is there. So I did not discuss all those speed controls because directly we can take any equation and directly we can do in the exam. Okay, because we know torque equation, it's more than sufficient. But here, of course, here also definitely you can do in the exam directly. But the thing is, in VVVF control, directly they are giving questions. So we have to remember one small, conclusion. Okay, that will reduce the time requirement in the exam. Okay, so here also we are not going to do anything great here. Okay, now see here, if I think of the speed. Okay, so what is the speed NR is going to be NS into 1 minus S. Okay, so what is NS actually here is going to be 120 F by P into 1 minus S. Okay, so if I can change frequency here, okay, now if I can change frequency, for example, frequency is reduced. Okay, if frequency is reduced, then synchronous speed is going to be reduced, so obviously NR has to be reduced. Okay, so in that way we are going to control. Okay, it means in our traction now, okay, everywhere we use this only. Okay, immediately after this problem and after this analysis and problems, I will enter into harmonics, then you will get a beautiful question. Okay, anyway, frequency is going to be variable here. But for example, if I reduce frequency by maintaining rated voltage, then what will happen? V by F. Okay, so if I reduce frequency for rated voltage, V by F is going to be more. So operating flux is going to be more. So my machine will go into deeper side of the saturation. Okay, so means we will try to, whenever you are trying to change frequency, we will try to change voltage also, such that V by F ratio will be maintained constant. Okay, now here one thing I have to tell you here, kind of super synchronous, subsynchronous. In the sense, for example, if the rated speed, synchronous speed of a machine is ns, okay, so if you are trying to achieve more than ns, what to be done? If you are trying to achieve less than ns, what to be done? Okay, less than ns we need to remember, because more than ns anyway we can do directly there. Okay, so for example, if you are trying to achieve less than ns, in the sense subsynchronous speeds. My meaning of subsynchronous is that synchronous speed is reduced compared to rated synchronous speed. Okay, so in this case, if you are trying to, actually this is going to be rated, for example, rated at no load condition. Okay, so if you are trying to achieve subsynchronous speeds, means that here frequency has to be reduced, means that voltage has to be reduced in order to maintain V by F ratio constant. So V by F ratio should be maintained constant, means that voltage is directly proportional to frequency. Keep it aside. Now for example, if you are trying to go to super synchronous speeds, okay, so if you are trying to achieve super synchronous, in the sense, for example, if the machine capacity at no load condition, if it is supposed to rotate nearer to 1000, if you are trying to achieve more than 1000, in the sense like 2000 and all, so frequency has to be increased or not? Yes. Okay, definitely frequency has to be increased, but can you increase voltage more than rated? No. Okay, basically in my machine design constraints, voltage is one of the design constraints, because depending upon the voltage, my dielectric, okay, insulation has to be designed. For example, if a machine is rated for 440 volts, okay, so definitely I can supply less than rated voltage, but I cannot increase beyond more than rated voltage. So what we do here in super synchronous speed, frequency we have to increase. Okay, so frequency we are going to increase, but voltage can be rated voltage only. So in super synchronous speed, there is no concept of maintaining V by F ratio constant, but frequency, let it increase, voltage will be same. Means that, what about V by F now? V by F is going to be reduced, means that operating flux is going to be reduced. Okay, let us think of subsynchronous speed. For example, subsynchronous speeds. Okay, I did not remember any equation. I'm not going to also in future, except one small thing. Okay, in subsynchronous speeds, voltage is directly proportional to frequency, because if you are reducing frequency, voltage also can be reduced to that extent. Okay, now if I see subsynchronous speed, what is the torque developed? full equation. Full equation is going to be m by omega s into I2 square R2 by S. What is I2? Think of like, that like RTH, XTH, X2, R2 by S. In that RTH, XTH were neglected. VTH became V1. So V1 will be there, X2 will be there, R2 by S will be there. In that, how much is I2? V1 divided by R2 by S square plus X2 square under root. I2 square is going to be this into R2 by S. Okay, in this we have to divide this into low slip region, high slip region. Okay, so in low slip region and high slip region, if you divide, okay, in low slip region means that slip is going to be low, less, means that it is running condition. Okay, so when slip is less, R2 by S is going to be more, so X2 can be neglected. So TD can be approximated to m by omega s into V1 square by R2 into S. Okay, in the high slip region, in this sense, let us think of starting only. So directly starting torque equal to m by omega s into high slip region. This will be less, this is more. X2 let us consider. So V1 square divided by X2 square into R2 by S is 1 because starting torque. Okay, now for example, let me ask you one thing. For example, previously we discussed the similar things in voltage control. Okay, for example, in our previous problem, previous problem, for example, if voltage is reduced to half. Okay, so if voltage is reduced to half, we can think of pull-out torque can be reduced to half square as our previous voltage control. Our starting torque will be reduced by half square, but we should not say running torque. Because who are you to decide running torque? Let load decide. Okay, so for example, if load torque requirement is more than your pull-out torque, rotor will be stopped. Okay, for example, if load torque requirement is less than our maximum capacity of machine torque, my machine will rotate, my motor will rotate the load. Okay, so means come to here. Okay, now TD directly proportional to m constant divided by omega s. Omega s in the sense 2 pi n by 60. N is directly proportional to frequency. Okay, so F into what is V? Subsynchronous region. V is directly proportional to F. So this is F square divided by R2 into S. Okay, so this R2 is anyway also constant only. Okay, now what is happening here? Directly proportional to SF. Okay, now frequency means that the moment, like for example, if I have 50 Hz frequency, for 50 Hz frequency for a given machine, synchronous speed is going to be constant, so directly proportional to SNS. So let us conclude. Actually, for this only I started this. Okay, for given torque slip frequency or slip speed is going to be constant. Keep this point in mind. Okay, so in subsynchronous region, in running conditions, for given torque, slip frequency or slip speed is going to be constant. Because just by having this, I don't know why they are giving 2 marks questions and all, just because of this, we got multiple times questions in GATE. Okay, now let us think of starting torque. Okay, starting torque directly proportional to number of phases we are not going to change, frequency we are going to change, voltage we are going to change, divided by X2 directly proportional frequency square into 1 by 1. Okay, so inversely proportional to frequency. Okay, now let me draw 2 characteristics. Let us think of pull-out torque, TEM, maximum torque. Okay, so how much is maximum torque? M by omega s into V1 square by 2x2. Okay, now directly proportional to. Are you changing number of phases? No. Okay, means of omega s, ns, 120 f by p, so directly proportional frequency into voltage divided by reactance. So pull-out torque is going to be constant. Pull-out torque is going to be constant. So let us combine these conclusions and let us draw just once, characteristics. What characteristics? Sectional characteristics. Torque slip or torque speed characteristics. Okay. Now let me think of, for example, this is NS. This is 0 speed. This is NR. Okay. So okay, for example, this is at rated voltage, rated frequency. Rated voltage, rated frequency. Now let us think of half rated voltage and half of rated frequency. Frequency is reduced or subsynchronous region and V by F ratio is constant. Okay, so what is TEM is going to be constant. So TEM is going to be same TEM for both black and blue. Okay, now let me calculate slip at which maximum torque occurs. Equal to R2 by X2, no? So directly proportional 1 by F, no? Okay, R2 is constant, X2 directly proportional frequency. So for example, frequency is half. Frequency is half. Slip at which maximum torque occurs will be doubled. So if I think of this as SMT1, SMT2 will be twice. This is going to be SMT2. So how much is SMT2? 2 times SMT1 for half of the rated frequency. Now, next thing is the moment I reduce frequency to half, what about synchronous speed? For that updated version is going to be half. So this is going to be NS2. Okay, so actually this slip is with respect to this, slip is with respect to this. Anyway, in detail course we can see, forget about it. Okay, basically my intention is rotor speed only. Okay, anyway, coming to the point, in the blue, so for the second case, speed of the synchronous speed is reduced, it has to start from here, and pull-out torque is going to be the same. Now let us think of starting torque. If you see here, starting torque, if frequency is reduced to half, my starting torque has to be doubled. Okay, so starting torque, if I think of this black is TST, blue is going to be 2 times TST. 2 times TST. Okay, so from here characteristic has to go like this. Okay, now if I have low torque requirement of constant low torque requirement. Now this speed and this is the speed. For the same low torque, speed of rotors are changed or not? Yes. Okay, basically this method is a wonderful method. Why? Because for example, if you compare with rated voltage control, if you reduce voltage supply, what's happening? Peak torque or maximum torque or pull-out torque or stalling torque is getting reduced by square times. What about starting torque is getting reduced? But now, for example, starting torque is increased. If you reduce frequency, and pull-out torque is going to be same. So this is the greatest advantage of this methodology. So that's why most of the cases we use this. Okay, now we will see problems. Now let us solve some problems on VVVF control. Okay, so the speed of 4-pole induction motor is controlled by varying the supply frequency while maintaining the ratio of supply voltage to frequency V by F constant. At rated frequency of 50 Hz and rated voltage of 400 volts, its speed is 1440 rpm. Find the speed at 30 Hz if the load torque is constant. Okay, so when the load torque remain constant, what was the equation we got previously? Slip speed should be constant or slip frequency should be constant. Okay, so here whenever it is operating at 1440, whenever it is operating at 1440, what is the rated speed? 4-pole, 50 Hz, 1500 rpm. So let us calculate SNS. So for example, what is S? Is going to be NS minus NR by NS. So what is slip speed here? SNS is going to be slip speed is going to be NS minus NR equal to how much? In the first case, 1500 minus rotor speed is 1440. Okay, so it's going to be 60 rpm. Okay, now this SNS should be same if you maintain V by F constant or not. Yes, for the same load. Okay, so what is the second time frequency is going to be 30 Hz. For 30 Hz, let me calculate NS2. Okay, so if I calculate NS2, how much is this? This is going to be 120 into frequency is 30 Hz divided by 120F divided by P, 4 pole. Okay, so is going to be 900 RPM. 900 RPM. Okay, so 900 RPM. Okay, so NS is 900 RPM in the new case. Okay, so what is rotor speed? Rotor speed equal to SNS. NS minus SNS. SNS should be same 60 RPM, right? Because slip speed, slip frequency should be constant. So in the speed of 900 RPM, 900 minus 60 is going to be 840 RPM. Okay, so if it is rotated at 840 RPM, then only SNS here will be 60 RPM. SNS in our new case also will be 60 RPM. Okay, so slip speed should be constant. So answer should be 840 RPM. Okay, now let us take one more question. See, 400 volts, 50 Hz, 4 pole, 1400 RPM, star connected squirrel cage induction motor has the following parameters referred to stator. So, resistance, reactances. Motor is controlled from a 3-phase VSI, voltage source inverter with constant V by F controller. The stator line to line voltage is RMS and frequency to obtain maximum torque at starting will be. Okay, so very simple. Okay, what is that? In VVVF control, slip frequency should be constant. Slip speed should be constant. Okay, so what he is asking? He is asking about the maximum torque. Okay, maximum torque will happen at slip at which maximum torque happen. So for example, directly you should not take what do you say, R2 by X2 is SMT, because X1 is also given. Okay, so let us draw the this is going to be R2 by S, and this is going to be X2, this is going to be X1 or XTH, whatever it may be, and this is going to be R1 or RTH. Okay, so about R1 they did not give any information, so it's going to be 0, and X1, X2 equal to 1.5 ohm. This is also going to be 1.5 ohm. Now PG is nothing but the power absorbed by the rotor, right? So when power absorbed by the rotor is maximum, PG is maximum, torque developed will be maximum. So when power absorbed by this is going to maximum by maximum power transfer theorem, R2 by this, yes, should be equal to 3 ohm. So that is SMT, slip at which maximum torque occurs. So R2 by SMT equal to magnitude of this is 3. So what is slip at which maximum torque occurs? Is going to be R2 is 1 ohm. So this is going to be 1 ohm. So means SMT equal to 1 by 3. Problem solved. Okay. So point here is very simple. Slip at which maximum torque occurs is 1 by 3. Okay. Now we know that slip frequency or slip speed is going to be constant. Now if you reduce frequency by some X percentage, voltage also should be reduced by X percentage only, such that V by F ratio will be maintained constant. Okay, so what's happening here? For example, S1 F1 should be equal to S2 F2 for a given torque. So now this torque is going to be maximum torque. So this is going to be SMT1 F1 should be equal to SMT2 into F2. What is SMT2? 1. Because if you observe here, the stator line to line voltage and frequency to obtain maximum torque at starting. At starting, this is going to be 1. This is going to be 1 by 3. 1 by 3 into frequency F1 is 50 Hz. So F2 is going to be 1 by 3 into 50 is going to be 16.66. Okay, if voltage is reduced by 1/3, frequency is reduced by 1/3, voltage also should be reduced by 1/3. Voltage is 400 by 3 is going to be 133. So answer will be this. Let us take one more problem. Actually, about this, even in random doubts. Okay, I thought whenever if any good questions come, any great questions come, I committed to do random doubts. okay, in the YouTube videos and all. Like here, this particular question, I think more than 50 members sent me till now, okay, because of small friction. I'll tell you. In a constant V by F control of induction motor, the ratio of V by F is maintained constant from 0 to base frequency. Okay, so from very low frequency range to base frequency range. Now, where V is the voltage applied to the motor at fundamental frequency F, which of the following relating to low frequency operation of the motor is true? Stator flux increases, decreases, blah blah blah. Now, point here is people feel if you maintain V by F ratio constant, will it maintain automatically flux constant or not? Yes or no? No. No. Basically, V by F should not be maintained constant, but E1 by F should be maintained constant. For example, if you think of our equivalent circuit, ideally my shunt branch along with resistance or without resistance, whatever it may be, it is going to be like this. Okay, so what in which branch is model to handle current which will set up the flux? This. Okay, now if you maintain V1 by F constant here, you means that does not mean that E1 by F. Actually, if you maintain voltage across this constant, automatically flux will be constant, but you are maintaining here constant. So, means around base speed. For example, if base frequency is 50 Hz, the rated frequency is 50 Hz, 50 Hz, 45 Hz, 40 Hz, 30 Hz, 35 Hz, 20 Hz, up to that it will be fine. For example, if you are thinking of operating your rotor at very less speed, under that conditions, frequency has to be reduced to maybe 2 Hz or 3 Hz or 5 Hz. Okay, so if your frequency is reduced that much, if you maintain voltage also is reduced to the same. For example, voltage frequency is very less frequency operation. So if you maintain voltage also reduced in the same proportion, this voltage minus drop is going to be this voltage. Anyway, induction motor always operated lagging positive voltage regulation and all. So if you maintain V by F ratio constant, because of this drop, this voltage will be less. Okay, for example, at rated voltage you don't observe much difference, but at low frequency, low voltage, so in the low voltage, maximum percentage of this voltage will be dropped here. Okay, so this voltage will be less. So means at low frequency region, if you maintain V by F ratio constant, operating flux here will be reduced, to be precise. Okay, that's why in our practical applications, means if you maintain V by F ratio constant at low frequency range, intentionally they will maintain more voltage than the proportion of the frequency reduction. Okay, so anyway, stator flux increases, gone case. Stator flux decreases from its rated value. Let us keep it aside. The motor saturates. The stator flux remain unchanged at its rated value. Okay, so specifically see here, we have to check the question. We have to understand the mindset of the paper setter. Okay, normally if you maintain V by F ratio constant, stator flux remain constant or not? Yes. Remain unchanged? Yes. Okay, but specifically they asked at very low frequency range. Automatically if you maintain V by F ratio constant at very less voltage, drop will be maximum percentage. Under that conditions, this will be reduced. So specifically they asked for low voltage, means that they are expecting you to analyze this way and stator flux decrease.